Looks like it's working. Well, it's isn't it university? It's a university. I just ripped it up. It's vanishing ink. It's vanishing ink. Okay. All right. I can sit down and enjoy coffee here. This one. Oh, okay.
A little bit outside, it's okay.
I think there's not much high energy here.
Still beams.
There beams, exactly, yes. What sugar? Yeah. 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 Okay. Oh, good. Hi, nice to meet you. So I'm trying to decide whether this is, do you use the 10-minute rule or the 20-minute rule? Yes, exactly. It was much nicer yesterday. Yeah, I kept feeling last Yeah, but it's hard to get, Santa Barbara, there used to be a direct Delta flight, Santa Barbara to Salt Lake. It's no longer. Santa Barbara did the built a new terminal and did a facelift of the unit from the airport, so they increased the landing fees, and Delta said, San Francisco, yeah. I'm flying back through LA, I went through San Francisco. No. None. Yeah, of course I do have that Learjet that I use, but I didn't, it was being serviced, so I couldn't do it, yeah. They have it from Seattle, but not Salt Lake. For some reason, exactly. Yeah, no idea. I was a postdoc at Cornell, and I took a flight with an airline called Bard Airways. I'm certain you've heard of them. Bard, yeah. So I went to I flew from Ithaca to Newark. But now I'll say, when I went to the Empire desk at the time, I said, when they were checking for Bard, the guy goes, oh, you do can, there's one of these signs where you push on them. And he said, I come from Cortland, which is a 20-minute drive. So the plane had 4 passenger seats.
So they give you talk to the
Yeah, so I was there listening, and so the pilot, the co-pilot, who was to fly 747s in the Air Force, was trying to learn to fly this thing. So he had his book out, you know. And then they had this squelch, you know, on their navigational thing, and it wasn't working, so they kept tapping this thing. And then I said, what's this hole in the dashboard here? And he said, oh, that's where we put the radar in the fore, we don't need it now. It was an interesting flight.
We can start. Attention, please. Today, I'm very glad to introduce the speaker, Professor Chris Palmström from UC Santa Barbara. He's a professor from electrical engineering and the materials departments. And when I know him as a leading expert in 3-5 semiconductor growth and their electronic property studies. So I'm going to read this short bio. So he received his PhD in electrical and electronic engineering from University of Leeds in England in 1979. He joined Belcore in 1985, and there he did his groundbreaking work on semiconductor surface semiconductor doping, growth of semiconductor heterostructures, and that's basically what I understand as the main contribution to the field that in semiconductor electronics. Mainly what I know is on 3-5. Correct me if that's not correct. Then in 1994, Dr. Palmström joined the University of Minnesota. In the fall of 2007, he moved to UC Santa Barbara. And actually his interest is very broad. He has done really solid and nice work on low-dimensional semiconductor devices. This Heuslers alloys, spintronic devices, including spin transport, magnetic counter junction-based devices, and also complex oxides, but too many to list actually. So today, let's hear his talk on the MB growth and electronic property of the Heuslers alloy films. Please go.
Thank you, Professor Sorelli. You know, with all that, I don't just say anything, I'm going home. I mean, she said everything now. So I should say a message here. She said, you know, I did all this beautiful, some MBE work. So if you ever worked in industry, you have to figure out how you can persuade your management to get what you want. And at that time, they had MBE growers when I joined. So I had to buy in 2 different years parts of the MBE, of my system, and it was called a controlled deposition system. It was not called an MBE machine, because that was not the right word to use, because they already had MBE machines. So anyway, I'll tell you a little bit about it, because I still have the machine, and I'll actually point out which one it is. So today I want to try and talk about something somewhat different, material system, because I think it's sort of exciting, and I'll tell you why I think it's exciting and different. And talk about this Heuslers compound. I should point out, I put all these funding agencies down. That's not to say they're all funding me simultaneously. Okay, what that really means is that you got $1 from each one at some point in your life career, you know. And what it is I'm really trying to acknowledge that when we had different funding sources, we're doing different things. So I'm afraid I can't say I'm that well funded at the moment. But it would be very nice to be. But anyway, a lot of work we're doing now is funded by the DOE and the DOD, Department of Defense. And a little bit of work is also funded by SRC in this standard program. Okay, so first of all, I did all the work. I had no collaborators. Okay, so the truth is the students, postdocs, and collaborators are everything, and I'm just the messenger. Okay, so please don't shoot the messenger, because that's me. Okay, so I had a number of graduate students and postdocs at UCSB who've been working on this. Jason Kawasaki is now a new faculty member at the University of Wisconsin. At the University of Minnesota, I had a number of students and postdocs as well. I've done a lot of the work I'm talking about is actually done in collaboration with Paul Kroll's group at Minnesota. All the transport measurements are already done there. So this has gone over a number of years here. Or at least put it that way, our groups aren't that big that we have 100 graduate students. It's just been one after the other type of thing. We've done some work also with the University of Lund in Sweden. I'll tell you a little bit about what we've been doing there, particularly Anders Mikkelsen's group and Craig Foley who's there. Some TM works I'll show you about, some transmission electron microscopy by Paul Voiles' group at Wisconsin. Done some theory with Bill Butler's group at the University of Alabama, and also some theory now with Anderson Gianotti's at the University of Delaware. Okay, so my group, we think about how to put things together, and we try to talk about making heterostructures from the bottom up, where we're trying to combine materials with different properties to try and make designer structures. And these can be metals, semiconductors, insulators, superconductors. We're doing some work with superconductors at the moment as well. And then magnetic properties, we're interested in ferromagnets, ferrimagnets, antiferromagnets, paramagnetics. So we might try and put materials together. We've had magnetic properties. We have done work, in fact, some of the first work I did with Heusler compounds was because they were ferromagnetic shape memory alloys. And the theorists came to me and said, can we grow this material in thin film form? And we said, sure, we'll try. And we actually made ferromagnetic shape memory thin films. So questions we're going to have is how we put these materials together, because we've got different crystal structures and properties. How well do they form? And can we make single crystals? And one of the things we always think about if you're in the sort of electronic materials is the interface is often your device. The interfaces are the most important part. Now, and what roles do they play? Okay, so I'm going to start with this Heusler compounds. I really knew. They were only discovered in 1903. Okay, so it's a little before my PhD. Okay, just a couple of years. The big thing about this was really that all these elements, manganese, tin, and copper in this case, are non-magnetic, but this compound was magnetic. So this is really why the Heusler became sort of interesting. You can look at this crystal structure. I'll keep talking about this crystal structure again. You can look at this and say, if I take the red and the green, I've got rock salt, and I've just put these blue atoms in the tetrahedral sites. So it's a cubic material. You can see here, this is what we call the full-Heusler. Another material system is what we call the half-Heusler, where every other of these blue are missing. And if you look at this material system, it really looks like zinc blende, which is a compound semiconductor, with these red atoms shoved in the octahedral sites. So the question is, do you think of this, when I look at these materials, do I think of them as metallic bonding? Do they look more like sp3, like you do in this compound semiconductor? And we'll talk about, that's where some of our properties come from. If I make this element y and x the same, I get this DO3 structure, which is often, you can think of as x2xz instead of x3z. And there's one called an inverse Heusler, where I put a y atom also on this sublattice here. So there are sort of classes of the materials really down by the structure to a large extent. Now, how many of you know about semiconductors? This is a test, by the way. Okay, so what are semiconductors? What materials do you make them out of? What groups? Group 4? 3, 5, 2, 6? But the periodic table is a hell of a lot bigger than that, right? So let's see what we can make Heuslers out of. Okay, so we are just expanding our horizons here on elements. Okay, so we can take this type of structure, and you can now include transition metals, the rare earths, and we can, the combination, this is what I'd say is, if you've done half of them, you can graduate from my group. Okay, there are about thousands of combinations. So it leaves an idea that you should be able to make lots of different things, keeping the same crystal structure, or related crystal structures, I should say. I should point out another thing, so because I'm going to come back to it. Think of the number, when you look at all these groups, do you think of the number of valence electrons we have? And what's going to be important, I'll point this out, is in fact the number of valence electrons per formula unit has a big effect on the electronic properties. So in fact these materials can be metals, equal, basically Fermi levels up here, you've got up and down spins. They can be magnetic, if you've got an imbalance of spins. Okay, they can be half metals, where I have for one spin metal, and for other spin is a semiconductor. The Fermi levels on the gap, and this should in principle give you, at the Fermi level, 100% spin polarization. So this is something we're really interested for spintronics, because now I can just have one spin that I'm playing with. So magnetic materials is something I'm going to talk about. Is really the number of valence electrons important here. And if I point out now, are they good ferromagnets? And let's plot it here, the Curie temperature for a number of these full-Heusler magnetic materials, things like cobalt-2 iron silicon, cobalt-2 manganese silicon. You can see here the Curie temperatures are around about 1,000 Kelvin. So that's pretty good, even if you want to do room temperature, compared to, for example, a dilute magnetic semiconductor, where it's well below room temperature, where it's magnetic. Okay, you can go further, and you can say for the half, if I wanted something which is a half metal, that means it should have integer number of Bohr magnetons per formula unit. That's going to give you one electron in this state. So if I take here, for example, if I take the number of valence electrons here, and just keep adding, going from titanium to vanadium, I add one, I should have one Bohr magneton. And it should be a half metal. And you can see these are for the half-Heuslers. The important number here is basically the number of Bohr magnetons should just be the atomic number minus number of valence electron minus 18. For the full-Heuslers, it's the number minus 24. And you can see here, a nice one I'm going to be coming back to a lot, cobalt-2 manganese silicon is supposed to be a half metal and have about 5 Bohr magnetons per formula unit. Okay, so we use MBE. What does MBE stand for? Megabuck evaporator. He's got, that's one solution. That's one. What's the next one? Molecular vaccine. That's a sort of poor answer. Mostly background equipment. He's got 2 out of 3. How many graduate students? How many graduate students here? Okay, many boring evenings. Okay. So that's the last use of this machine. Okay. So we put the elemental sources we want. You put them in crucibles and heaters around them to evaporate. And the shutter in front opens and closes to let the flux hit your sample that sits on a heated stage here. And then we have liquid nitrogen. You can see this blue stuff is sort of internal liquid nitrogen cryopaneling to keep good vacuum. Typically our growth background pressure is below 10 to minus 10 torr. And we can, another nice thing is you can use electron diffraction to actually look at what you're doing while you grow. And this is my small system. Okay, so we've connected together a few of these different pieces of equipment so we can do experiments that do materials. One of the things we worry about is cross-contamination. Contamination of one element into what you're trying to grow. So typically down here we have our 3-5 semiconductor growth chamber, and we can transfer the sample from here down the line to other chambers. So just as I go down it, here we have Lorentz electron diffraction and Auger electron spectroscopy. We have some X-ray metal deposition here. We have X-ray photoelectron spectroscopy we can do here. We can do minute optic Kerr effect in situ for looking at magnetic materials. Coming down here, we've actually got 3 scanning probes attached. to the system, a low temperature one, a variable temperature one, and one which will drop into a vector magnet. Here we have now another MBE system where we grow some Heuslers. We can transfer down, we have some more depositions down here, and another chamber here. Here we have another MBE, we grow other Heuslers. Here we're growing some semiconducting Heuslers. Here's magnetic Heuslers. We can grow oxides over here, or nitrides, we're doing a little bit of work. And down here we're using chemical beam epitaxy to grow arsenide and phosphide compound semiconductors. But basically you can transfer the sample back and forth. We try to go from the clean systems to the dirtier systems, and not back again without cleaning the... How long is it?
Yeah.
It's about this, no. It's about 20 meters.
Boring evenings at that.
How many boring evenings? Many boring evenings, right, to do this. But basically what we're trying to do is to do in situ, grow stuff and measure it and characterize it. It's really the thing that goes on with it. Okay, so it looks something like that. So you can see many knuckles to be done when you do the bolts, if you're doing them, and it's basically interconnected all the way down. Every machine can run independently, so when one machine goes down, you can fix it without affecting too much the other machines. Okay, so let's start off with this concept of a simple thing, the spin FET, which I would argue that no one's really made a spin FET yet that really works, okay? But the concept is good because it gives us a reason why we're trying to do what we do. Okay, so the idea here is, this is sort of a dot or dust, you really call it a spin optoelectronic modulator rather than spin FET, but the idea is you have a ferromagnetic contact, you can inject spins, transport them in a channel, and detect, using another ferromagnetic contact, the orientation of the spin, and in between, if you have a gate due to spin orbiter coupling, you can actually use a rush bar to manipulate those spins. So you can get rotation of the spins, and this is the idea that you measure spin as well as charge on the device, of the electron. So the whole idea is, can we actually inject and can we detect the spins? And does this really work? And you're going to tell me it works fantastically for every material system. Okay. So we're going to worry first about just doing these contacts. That's what we spend a lot of time. So what we'd like to do is to make single crystal contacts. So obviously if you've got a metal, it's going to have different bonding, different cross structure than the semiconductor. We would like to have single crystal interfaces of growth, always one lattice matching, one composition control. And we need to worry about thermodynamic stability. If I put a metal on top of a semiconductor, is it thermodynamically stable? Will it react or not? And we need to really basically limit interfacial reaction, and we need to control the properties of our films. So years ago we started all of this, and we said, well, iron is a very good ferromagnet. Iron, if you look at it, if I put 4 unit cells of iron on top of gallium arsenide, the mismatch is 1.4%. So it looks very good for epitaxy. It's not a big mismatch. So the things we're going to worry about if we put iron down is, what's the spin polarization, which I've mentioned before what iron is, was 42%. What's the band alignment, band structure alignment between the ferromagnet and the semiconductor. And once we've got the spins in, how far do they diffuse in the semiconductor? Those are all intrinsic properties. Extrinsic are that people reckon or thought that if you have any interfacial reaction, you'll get spin flip scattering. So the common belief was that any interfacial reaction killed your spin injection. That was sort of a belief. Now,
Question?
Yep.
When you say no interfacial reaction, are you talking about van der Waals bonding, or what do you mean?
Okay. So you see, I'm doing a little bit more chemistry than van der Waals. Okay, but basically any bonding at that interface. If I get a phase, if I just take very simply this argument I'm going to take now. Take iron, put on gallium arsenide. How does the iron bond to the gallium arsenide? And does it form, for example, a thin layer of iron arsenic? If it's one atomic layer of iron arsenic, that's, is antiferromagnet. So is that good or bad? First thing you say it's bad. If I get more and iron starts diffusing into the gallium arsenide, and what I'm going to point out here, if I show you the ternary phase diagram that we believe is the correct one, For something to be stable, there must be a tie line, say from iron to gallium arsenide, and there's no tie line, which says it's not thermodynamically stable. That says that if I put iron down, I expect it to react. And in fact, what I expect to get is iron 3 gallium and iron 2 arsenic. So that tells me immediately that thermodynamically, this is not a stable interface. Okay? And I'm not going about the van der Waals yet. Van der Waals you always get. This is worse than van der Waals. Okay? But what does it do to us? So what it says is to be able to grow this, to stop or minimize reactions, we have to do it by keeping it relatively cool. The higher temperature we take it, the more it's going to be reacting. So we try and do that. So then, of course, I'm going to go to the next step. Okay? I showed you all the bulk. Okay? So if you believe in Wolfgang Pauli, God made the bulk, the surface was invented by the devil. Okay? It's a very good statement when you start doing surface science. Okay? It's a good thing to have. Just remember that it's all sent to try here. So if I go and I say I'm going to start with gallium arsenide. If I take the 001 surface of gallium arsenide, here's a phase diagram. Depending on the arsenic to gallium flux you have, I can get lots of different surface reconstructions on that surface. So for example, the typical one, this we call it a 2x4 or C2x8. This is what you typically have when you're growing an MBE, is the arsenic is terminated by 2 arsenic diamonds on the top surface here, another arsenic diamond in the third layer down. This is sort of a typical surface. If you cool it down under arsenic, you get this C4x4 surface, which is a complete monolayer of arsenic and 3/4 of monolayer of arsenic diamonds on top. Now, if I'm going to grow my iron on top, which surface do I want to use? Do I want to specifically go for any of these reconstructions, or will anything work? You don't know, right? You don't know. So, okay, I'm going to tell you first about one we've done. This is the easiest surface to form when you've done MBE, because you just cool down a little bit in arsenic and you shut the arsenic off and take it out. All the others you have to work to get different surface reconstructions more. And I'll show you here we've actually grown iron epitaxially on top of gallium arsenide. This is a cross-sectional, high-angle, dark field scanning transmission electron microscope image. This is iron on gallium arsenide. Now, if I talk about the 1,1 direction and the 1,10, those are just looking at 2 different 90 degrees on of the gallium arsenide. If you actually look, if I do look on the 1,1 I have for the arsenic diamond rows, and the arsenic atomic rows are this gallium arsenic. So this would be the 1,1 So if I go here, this 1,1 that would be a gallium atom, that would be an arsenic atom underneath. You rotate 90 degrees, it's arsenic up, gallium down. It just comes from the zinc blende structure. But if you look at these two interfaces, this is the iron, here's the gallium arsenide. Do those two, if I put them side by side, look the same? The test. Okay, this is question number 3. If you might notice, there's some additional contrast right in there you don't see there. It looks slightly different. So we actually, this is work from Susan Stemmer's group at UCSB's microscopists, where you then try and put together an atomic model of the surface here, this interface. And you can see here, looking down the 1,1 you see the ions on top of an arsenic. If you look at down the 1,1 it's on 1,10 direction, the iron is straddling the arsenic on the top. So in 3 dimensions, it looks a little bit more like that. It always looks sexier that way, right? So we're just thinking that's what the arsenic is actually, the iron is doing, is bonding to the arsenic at that surface. Okay. So of course you have arguments with other people in literature who have a different model, but this is what we believe the model is. Okay. So that was us saying we can grow iron, it works, we can spin inject from it, it all works well, but you'd like something that's thermodynamically stable. So what I actually point out here is if I said what I'm right about this ternary phase diagram, this tie line suggests that iron 3 gallium should be stable on gallium arsenide. That's what the thermodynamics is telling you. So what we try to do then is say the normal phase, if you look at the iron gallium phase diagram at room temperature, is this one. But if you look at some of the high temperature phases, there's this iron 3 gallium, which is this DO3 structure, which you can think of as a Heusler iron 2 iron gallium If I look at that, the mismatch to gallium arsenide is something like 2%, 2.8%. Could we stabilize this on top of the gallium arsenide? And does it work? And it's got a Curie temperature of about 900 K. Okay, so here we go. We come back to the question. Do I start with an arsenic-rich surface, gallium-rich surface, how arsenic-rich, how gallium-rich? And when I start the iron 3 gallium, if you look at it, it's iron, gallium, iron, gallium atomic layers. Which layer do you want to start with? Do I start with iron first, gallium first, or do I co-deposit iron and gallium? And does it make a difference? So that's one thing we sort of worry about. Other thing we have to do to be able to get this to work, we would like to have, for the spin injection, a contact. When you put metal down on gallium arsenide, you always get what's called a Schottky barrier. I hope you all know what a Schottky barrier is. Okay? You all know a Schottky barrier. Good. So we get a Schottky barrier, typically a barrier height is about 0.7 eV. And what we've done is we have to dope the gallium arsenide very heavily just below the contact. So we'd grow a 510 to the 18 layer here to make this thin enough to be able to tunnel through. If we don't, we get a very, very large depletion region and you don't get any tunneling. So basically we've done some design of just the semiconductor doping profile to get this to work. And we also actually have a little bit of a quantum well here, a 2D gas probably right underneath, for the amount of electrons we have in there. Okay, and then what we're going to do is measure, do we have spins or not? So here's our pseudo spin FET. Okay, this is work that Paul Kroll's been doing at the University of Minnesota. He takes our samples and makes this structure up. So here's basically the idea. You pass a current from this, say, contact C, electron from C to A, and we're going to measure the voltage from D to E as you apply an in-plane magnetic field. So you can now make these two are now the ferromagnetic contacts, and you can, with the applied field, you can make them parallel or anti-parallel. And then what you're going to do is measure, and I'll talk about that in a moment here, the difference in the voltage that we measure here between them in the parallel and anti-parallel state. If you apply a perpendicular field, you can make these spins precess as you go across from one to the other. So that's a Hanley measurement. So that's another way of measuring that you have spin transport. We can also, in fact, put this voltage probe, put the current go underneath as well, the contact as well. You can do that. You can use magneto-optic Kerr effect. Scott Crooker, for example, did a lot of this, looking at the spin polarized electrons in the gallium arsenide to also prove they have spins. And of course, you can change a bias on these contacts. Okay, so here's the idea. What we're going to do is basically, if I, for example, have an electron current going from the semiconductor into this contact, if you have a half metal, only majority spins have density states to go into, so you leave behind minority spins, and these will then diffuse in this semiconductor. So what will happen, the majority spins will flow across, and the minority spins left behind will now diffuse towards this contact C. And you're going to measure this voltage. So what we do then is measure this voltage from the parallel and anti-parallel state. You're measuring the chemical potential, say for the up spins, and then for the other one you're spinning for the down spins when you flip the spins in that ferromagnetic contact. So this is our measurement of what our spin transport's doing. Spin polarization. So here now, as to show an example, this is now this delta V that we measure between C and D. This is now when they are anti-parallel, and then they're parallel, anti-parallel, and parallel when you do the magnetic field. And this is the Hanley measurement of the perpendicular field, showing that the Hanley actually follows exactly the same that we get for the spin valve measurement. Okay, so now let's look at the example of this iron 3 gallium we grew, and say here, again cross-sectional high and dark field STEM image. Here's the iron 3 gallium on an arsenic-rich interface. This is now looking on the 1-10 direction, and this is perpendicular on the 110. And here's the gallium-rich interface we grew, and you can see here and here. Do these look different? Votes. How many say different? Oh, not different. It's different. Okay, you all agree. And in fact, you can look more carefully. Do you notice this? There's something funny there. That, we believe, is the remnants from the C8x2 gallium-rich surface of gallium arsenide before we put the iron 3 gallium down. But if I look at our spin signal as a function of bias, you see virtually nothing for the arsenic-rich interfaces. And we saw a nice signal when you had the gallium-rich interface. So this is telling us that that interface is very important for the spin injection and the spin transport. So one of them is injection, it's a forward bias, reverse bias, it is just changing the direction of the current through that contact.
But you cannot foresee it. I mean, can you guess that this is what will happen?
Well, it depends. I'm not a theorist, so I don't need to guess. No, I'm allowed to guess. But the theorist is supposed to tell me I'm right or wrong, right? Is that the right, or predict? Okay. Do we expect, the only one I can say is that iron 3 gallium is a ferromagnet. So gallium-rich iron gallium compounds tend to be magnetic. Iron arsenic tend to be antiferromagnetic. So I would, first reaction, say that if I have iron arsenic at the interface, I'm probably going to get less spin injection. But I didn't know that a priori. That's, with hindsight, I can use it as a hand-waving argument. Okay, so now what this has done to us is say, well, let's look at other compounds, these Heusler compounds, which basically, this iron 3 gallium is basically a Heusler compound. This is this guy here. And we can now look at other, there's a whole slew of them. I said there were thousands of them. And you can see here, if I just plotted some of them up, so these are the aluminides, this traditional metal manganese aluminum. You can see here I'm spanning nearly all the lattice parameters of the 3-5 semiconductors. So we should be able to play games to actually get things to match. So typically, cobalt to manganese silicon and excuse me, say iron 3 silicon, for example, or cobalt 2, or iron silicon, which I think iron silicon should be here somewhere. Yep. I don't see it there, but it should be. It's actually close to gallium arsenide. So here now is the cobalt to manganese silicon band diagram. This is calculated, not measured. Okay, and you can see here, majority of spins is metallic, minority of spins is a semiconductor. And the gap here is normally something of the order of 1 eV. And we can sort of draw this as density of states, as the reds for majority and blue for minority. And we see here we have the band gap for minorities. And I pointed out here the mismatch to gallium arsenide is 0.06%. So it's a very good lattice match. So we should like to grow this on gallium arsenide. Okay, now let's go back a little bit and worry a bit about defects. So theorists come up and say, how good ordering do we need for these different crystal structures? And what I'm going to point out here is that if cobalt goes on a manganese site, so cobalt on a manganese site, that would decrease the spin polarization dramatically. Manganese on a cobalt site, not so much of a problem. Manganese silicon disorder, if I disorder these, I end up with B2 crystal structures, basically cesium chloride. Shouldn't have too much effect on the spin polarization. And of course that's all about the bulk. The surfaces, in theory, I'll tell you, it's very important what the surface termination is, whether or not you keep the spin polarization at the surface. Okay, so here's showing we've actually grown cobalt to manganese silicon. This is reflection of electron diffraction. These streaks say it's relatively flat and it's nice and crystalline. It's grown up to 170 degrees C. Here's a cross-sectional TO image. You can see the gallium arsenide. Here's a cobalt to manganese silicon. And if you look very carefully, you might see it looks slightly different up here than it does down there. See, this sort of checkerboard pattern is a little different. This is primarily L21, which is a Heuslers structure. This down here is B2, as we can tell. Magnetically, we have uniaxial anisotropy. The easy axis along the 110. These are reed oscillations that just suggest this layer by layer growth while we're growing it.
That's in plane?
In plane, in plane. These are all in plane. Okay, so now comes a thing, again like I did for the iron 3 gallium, what happens if we grow this on the gallium arsenide? Do we worry about the surface of the gallium arsenide, do I start off with, say, cobalt first, look at the stacking sequence, manganese, silicon, cobalt, manganese, silicon, cobalt, or do I start with manganese, silicon first? Does it make a difference? Should it make a difference? So one of the experiments we've done is to use X-ray photospectroscopy, since we have this in our system, and we're going to grow it atomic layer by atomic layer and use the X-ray photospectroscopy to measure the signal from the film and the signal from the substrate, the attenuation of the substrate. This is a very surface-sensitive technique. So we're going to do one where we start with manganese silicon first, then cobalt, then manganese silicon, then cobalt. And the other one, we're going to go cobalt first, manganese silicon, cobalt, manganese silicon. So I'm just going to summarize the results. Let's start off with, if I do gallium arsenide, the C4x4 surface, I put manganese silicon down. I can see model IXPS data to show we have manganese silicon with a little bit of gallium arsenic riding on the surface. So there is a little bit of reaction there. We put the cobalt down. We see the cobalt goes on top of the manganese silicon, and you get, again, the gallium arsenide rides on top. So the surface energy of gallium arsenide is lower than that of the cobalt or metal. Now if we do cobalt first, we find the cobalt goes down, get a bit of gallium arsenic on the surface. Put manganese silicon down, we find no attenuation of the cobalt signal. So the manganese silicon actually went underneath the cobalt. So what happens is it didn't matter which way around we went, we end up with manganese silicon at the interface. And then of course, a chemist will tell you chemistry dominates. So it's really the manganese silicon, the reaction of probably the manganese with gallium arsenide is what's dominating it. Okay, so now...
Sorry, Chris, back to this. So you capping with gallium arsenide?
No, this is a result of...
One of these burrowing things?
Well, it's not really burrowing. Well, I think what's happening is the top surface monolayer is reacting a little bit and the gallium and arsenic are riding up. Okay. And it's basically about one monolayer of coverage, or submonolayer. Okay, so here now is a cross-sectional TEM. This is our cobalt 2 manganese silicon. There's another one here. This is the gallium arsenide. Looks very sharp. This is along the 1110. Here's the 110. Looks pretty good. So now you'd say, well, I had all these models and said the manganese silicon things were at the interface. Can we actually really determine what's going on here? So you go and you talk to a theorist, to Bill Butler, and you say, look, I got cobalt, I got manganese, I got silicon, I got gallium, and I got arsenic. Tell me what the interface would look like. It's only 5 elements. Come on. The periodic table is a lot bigger than that. So what happens? So the theorists immediately start off and say, we'll calculate the minimum energy, right? The interface of the minimum energy. And of course they start doing this, and then of course you start different positions for all the atoms, you try and get them to minimum energy. And you find out there's no global minimum, right? There's no real strong minimum. So then they change concepts of how you do it. Now what you do is you say, well, you talk to the TM person, did some yields and did other things, and you start trying to fit a model of an interface with atoms mixing up a little bit to try and simulate the TM image that you see. Okay, so here now is a model, and you can see here they're trying to simulate this experiment. This is a theoretical image. They're close. I would say they're not perfectly matched. This was model number 90. Okay. Model number 92 might have been slightly better. Okay. But basically what it's saying, it's not easy to say this is what you should have. Right? But all we can say is that there are a few layers of exchange of atoms. It appears to be, seems to be in agreement here.
Did it require any vacancies?
This did not require vacancies, right? But I mean, you do all of this with what the model does. I say all the things are subtle, and one of the biggest problems was with the EELS data. They couldn't see silicon, so it was very difficult to say where the silicon atom was. And that's why you're trying to use the relative intensities in this image to say what could be silicon, what was not silicon. Okay, now, what effect would all this have on if we made a spin valve? Okay, so let's do a comparison. So this is what we were doing in the past was iron. Here's a spin valve signal. Here is a cobalt-2 manganese silicon contact. Okay, another thing that Paul Kroll's been doing is putting a bias on the detector. It can change the sensitivity of the detector. So if you go with a bias detector, you nearly go up by over a factor of 4 in the signal level that you've got. Now you can see immediately that cobalt-2 manganese silicon was a much better spin injector than the iron was. And iron before this was our highest spin injection efficiency. Okay, so now let's come back to this thing. If I do cobalt-2 manganese silicon, what happens if I decided to add iron, say do cobalt-2 iron silicon? I've added one valence electron. The formula unit if I did that, or go in between. In fact, we could go in between. Let's just add iron, mixing sort of manganese. I should be able to go from cobalt-2 manganese silicon to cobalt-2 iron silicon. And if I think of this as just adding electrons, all I'm doing is move the Fermi level up. Right? Simple model. Now, if you do that, if you look at this, which said this was predominantly the majority of spins were red. If I go far enough to cobalt-2 iron silicon, I'm no longer a half metal, and the majority, and we now should have higher density of down spins if these were up spins. So it should change the spin polarization. And then it should be sort of pretty low when you're in the middle here, when you've moved these things up. Okay, so that was sort of a thought. The mismatch, 0.09%, so it all should still be good lattice match. And we can grow it. And we've grown them, and here now is from these lateral spin valve measurements, you can see here, cobalt-2 manganese silicon, model this out from the spin drift diffusion model, gets somewhere around about 60 to 70% spin polarization. Add, say, 30% iron, it goes down. Pure iron is down here. And cobalt-2 iron silicon is the opposite side. Not quite as high a signal as this, but pretty close. So it's, yeah.
Excuse me, what is the conductivity of the
What's the conductivity?
Is it close to gallium arsenide?
Oh no, the conductivity is much lower. So much higher conductivity. So conductivity is probably something like 100 micron centimeters, something like that.
So how do you explain the spin injection?
The tunnel barrier of the Schottky. The tunnel barrier of the Schottky gives us a spin-dependent resistance. So don't forget, it's not an ohmic contact. It's a tunneling contact. So it's a ballistic transport into the gallium arsenide. So that model that is put out and said it was all conductivity mismatch is not relevant if I can do ballistic transport going in. So
this barrier you can calculate?
Yeah, the barrier, we've actually measured it. I can go back here, since you're asking that question, I have to go back several slides. Sorry about that. This is it. This is it. The barrier is 0.7 EV, and we made this thin enough to tunnel through it. Okay, by doping.
The barrier with any ferromagnet?
Well, just about anything you put on gallium arsenide is going to be between 0.6 and 0.9 EV. Because the Fermi level pinning position from surface states is more or less mid-cap in gallium. So that's gallium arsenide. So that's why it works. All right, let's go zipping through. Try and go fast here. Back to
Chris,
work.
one hot topic. What about lateral momentum mismatch between two materials?
Oh, yes. Okay, so that is to do with, okay, so now let's, if I come back to, let's come back and have this thought. If I look at the Heusler, it's got they tend to have the electron pocket, if it's indirect, it's going to be out at X, which is a pretty good match for going directly in to gallium arsenide to gamma, if you're doing that. It's not a perfect match in plane. You think of the in-plane momentum mismatch, so at least I've got the pocket in the right direction. If I do another crystallographic direction, I think you may have to worry. But we don't have a, so one of the things, this is to do with the band structure alignment between the two materials. Right?
Sorry, I don't understand your comment. If the Heusler is out of X, it's some, there's So non-zero.
It's non-zero perpendicular, so that's a reflection.
Non-zero component along the total one, right?
Right, it's non-zero along area 1, we're going in area 1. So in plane, I can match my momenta, but I have a mismatch perpendicular, which gives me just a larger reflection coefficient. Right? So,
Right, I'm not understanding the part about how you can match in plane.
well, the in-plane is very basically saying if my pocket is, if it looks like an ellipsoid at gamma, I'm a pretty small pocket too. So I'm not trying to go out, let's say, at L. I'm still aligned along X for those electrons. So the in-plane momenta could be 0.
Okay.
That's what I'm getting at. Okay. Okay. So we did this, and now you ask the next question. Okay, temperature pendants, it dives, right? You go from low temperature up to room temperature, looks pretty small. And it's because these devices are big. These are sort of 10 micron separation. If you make the device small, so that the contacts are close, like 250 nanometer separation, this is what Paul's done. We use cobalt-2 iron injector here. You can get the spin valve signal even at room temperature. And the comment here was that this is what was happening, 5 years ago. This is what got our low temperature. So this is really, it really does work. I'll make an interesting comment here. Cobalt-2 iron silicon works. It gives a lower spin signal, but lower noise than if you use cobalt-2 manganese silicon. And we believe the manganese is doing a little bit of diffusion, and I've shown some SIMS results, if you want to say that, into gallium arsenide, and it's actually giving us more noise, although a larger signal. Okay, so here what is it really it's all due to is basically the spin lifetime in gallium arsenide drops like a bullet with temperature. And that's really what we're seeing, not the spin injection changing as much as the spin lifetime in the gallium arsenide. Okay, so now let me point out that with Heuslers, the other thing they can do is semiconducting. So it's another of these, particularly if these half-Heuslers, if you have 8 or 18 electrons. And if I sort of think about this, you go from diamond is 4, 3 5s are 8, and half-Heuslers can be 8 or 18. They should be semiconducting. And you can sort of think of them very simply as being, sort of, for example, cobalt, titanium, antimony. You can think of this being cobalt, antimony, zinc blend with titanium stuffed in the octahedral sites. This titanium 4+. And then you end up being neutral, and basically if you go from the chemistry, you should then basically end up with a band gap. And in fact, it's predicted to have about a 1 eV band gap. So cobalt, titanium, antimony, and nickel, titanium, tin, 18 valence electrons are all normally semiconducting, and if you go add an electron, you'll go n-type, or take one away, you go p-type. Okay, so cobalt, titanium, antimony, lattice parameter 5.888 angstroms, very close to indium phosphide. So we should then in principle be able to grow this on an indium phosphide. And this is the band structure. Again, pointing out this one here, you can see this out at X is where your electron pocket is for the conduction band. Here's the valence band. And bulk samples tend to have high chiral concentration. So we try growing this material. And what we've done is we've used indium phosphide, grown an indium aluminum arsenide, indium gallium arsenide buffer layer, and then transferred down and grown this cobalt titanium antimony or cobalt nickel titanium antimony. I'll talk about cobalt titanium antimony today. Diffraction pattern looks nice from the read. We can see nice interference fringes in the X-ray diffraction, saying it looks like a good single crystal film. Our growth rates are really high, 15 nanometers per hour. No one's going to jump up and down for that, but as we run slowly. Here now we can do STM on the surfaces. We see different surface reconstructions on the surface. We're trying to now identify what the atomic structure really is. We get this read oscillations during growth, so we show layer by layer growth. I won't go into the details, but we're trying to understand these. We can adjust. The nice thing about growing this material, we can grow with excess antimony if you grow hot enough, because it doesn't stick unless it reacts. And then we can actually get a surface phase diagram, just depending on the antimony flux and substrate temperature. Okay, so now what about the properties? So here I've plotted the carrier densities we've measured in our films and compare, this is for silicon of the same carrier density, and here's cobalt, titanium, antimony. So for about, lowest we got down to is maybe 5 10 to the 17, and we get mobility to the room temperature of about 500. So this is about the same as that of silicon. So we think this is pretty exciting, because now we have a completely different material with somewhat similar properties to silicon. You can think of it as the same indirect type band gap semiconductor. Okay, so the last thing I want to mention to you is this prediction that should be topological. The sum should be a topological material. In other words, they should have a Dirac cone. Okay. So one of the ideas here is if you have a trivial insulator, you'll have the S and P. P will be your P bands will be your valence band. S will be in your conduction band. But if you get enough spin orbit, you can invert this and get the S bands below the P's, so that your material, if it's topological insulator, you have a gap where you'll have basically P-type conduction band, S-like states down in the valence band. And then if that happens, you are supposed to then have on the surface a surface state, which is basically this Dirac cone, which should have spin and momentum locked, okay, at the surface. So this is now so now here the theory, all of these up here are trivial. These down here are supposed to be topological. So this is basically, the larger the atomic number, you can think of this, the more spin orbit, the more topological it's going to be. We decided to pick platinum, lutetium, antimony, because it's right on the border between the trivial and topological. And you can see it's closely lattice matched to indium antimonide. So can we grow this material and can we figure out if it's actually topological? Okay. Unfortunately, I don't have it here. It's not, doesn't in the bulk, it's zero gap semiconductor, unstrained, or it's a semi-metal. Theory suggests if we can strain it, we can open up a gap. And that's something we're going to try and do. First, we try just growing it to see if we can grow it as good as possible and not worry whether or not we have bulk conduction. So here now, just show you here the close match to indium antimonide. In fact, if we put a little bit of aluminum in, indium, aluminum, antimonide, we can perfectly lattice match to it. Okay, so can we grow it? Yes, we can. Same like we did the cobalt, titanium, antimony. We've grown it. It shows nice diffraction patterns, get layer by layer growth. We get different surface reconstructions, and we've grown this on aluminum, indium, antimonide. And here I can show you an STM image of it. It looks pretty nice. You haven't yet got an atomic structure of this yet, but we'll just show you that we can actually look at it and try and interpret what's going to go on. We're doing some scanning spectroscopy on it as well. And then what we want to do to show the topological state is to use angular resolved photoemission spectroscopy. So we want to take this into a synchrotron to do the experiment. So this is just to show you what we're going to do, take photons in and look at analyze the electrons coming off. We measure then to see if it's actually going to measure the band structure of the material. So this is to do this, what we wanted to do was we wanted to use an antimony cap. We can put antimony on top of this platinum, lutetium antimony, heat it up and get the antimony to blow off and give us a clean surface. Okay? So why would you do this? You're graduate students. Why would you choose? There are synchrotrons all over the world, right? You could go to Stanford, to Berkeley, to Sweden, to France. Where would you choose?
The closest.
The closest, yes. But as an advisor,
One of the best food.
one of the best food, you can tell the different attitudes. So as an advisor, I go for the cheapest. Okay? So for me, so the simple solution is you say to a student, we have an international NSF travel grants for students. You can go to Sweden for free, or you can go to Berkeley and I have to pay for you. You're going to Sweden. Okay? So this experiment was all done at the Max Lab in Lund in Sweden. We had to develop, so we had to take the sample out. You have to,
How do you know that surface is still intact.
How we do that? So what we did is this. We're doing this.
Sodium is a long way.
It's a long way. It's a long way, and they speak funny language and they eat strange food. You know, with all of these things you don't want, but you have to survive. You know, you have to deal with them. So what we do, we put antimony down. If you go cold enough, we can grow antimony, and when we can heat it up, if you go up to about 350, 400 degrees C, the antimony evaporates. But the problem we had was that this plant-medicinal antimony reacted with this aluminum indium antimonide when you did that. So we put a little bit of gadolinium antimonide as a diffusion barrier in between. And that allowed us to go hot enough, blow it off. And here's a lead pattern taken at UCSB before we capped. Here's a lead pattern with a slightly different lead system done at Max Lab after we removed the cap. And then you can look and see, do you see oxygen, carbon, or anything else on the surface? But we can actually see from the diffraction pattern, we've got the same film. Okay, so what is it we're really wanting to do? We're going to now change photon energy. If you change the photon energy, we can actually look, this is calculated band structure, where we see the S states down here. This is the conduction band here. This is this zero gap. And if we're changing, we can then do cuts. Look at the bulk band structure. You can see if I go at this point, you'll see this. And then you're looking down here. If you look in plane, I'd see this if I'm changing out of plane. So the bulk bands, as I change, the photon energy will go down if I'm looking just in the Z, in the perpendicular direction. The surface state should not change. And we're going to look for this blue surface state, which we've just drawn in there. There's no theory for that surface state except there's supposed to be one there. So what we're looking for, the signature, is there should be no outer plane dispersion to look like a Dirac cone. It should be linear with no partner bands, and we should be able to have spin momentum locking, meaning there should be a helical spin around these things. Okay, so here now is this change in the photon energy, and you can maybe see this is the raw data, and this is the second derivative. You might see there are some bands as you would go up in energy that are moving down. And you can see some here, these are not changing. So those are surface states, and the others are bulk states. This is how we're determining what's a surface state and what is not. So this is that's a snapshot of this. This is sort of the surface state. This blue and this green. These green. These are look like Rashba split states. And then these are the bulk states as we change the photon energy going down. Okay. So now what we wanted to do was to see if I change the binding energy. So this is a KZ perpendicular. If it's a surface state, that should be a straight line, because your reciprocal lattice of a plane is a nice straight line rather than a dot. So that tells us it's a surface state. And if I change the photon energy, the separation in plane, which is what we plotted here, will change. So if I do this, we're going to try this little calculation here and see if this thing working. And here's the data. You might be able to see that those vertical lines are separating further and further. You see them moving out? Okay, so this has been plotted here on this plot. Okay, so what that's saying, this is just a snapshot taking different binding energies. You can see if you do this binding energy plot here, we get a Dirac cone. The point is about 240 millielectron volts above our Fermi level. Just extrapolating. So at least it looks like we've got a Dirac cone. And the final thing we need to try and figure out is it spin polarized? So now what we've done is spin polarized upwards, and here is taken, this is the top of that cone in plane if you're looking at. I'm just cutting it about here. And what we've done is do spin polarized. Let's take this one here, this red arrow. If you now look at the dispersion curves here, energy dispersion curves, this is now looking at the spin polarization. You see there's red and then blue. So that's saying that this surface state is going in this direction. The arrow is going, we're looking at the point of the arrow. Here we're looking at the tail of the arrow, the opposite directions. If I look at this point, this blue one, you'll see here, this is point 2 here, you'll see it's blue-red. So this corresponds now to a spin that's going helically around here. If you look at this point here, we're not sensitive to any spins in this direction, and you'll should see nothing. So this, we believe, is the first demonstration, direct demonstration, that this is a topological material. And we see that surface state. And then someone's asked me about Rashba bands. We believe this down here is some surface states which are Rashba-like. Okay, so I should really conclude here. We're running out of time, but it's basically saying we've demonstrated we can actually make these Heuslers materials. We can adjust their properties. In fact, I've already talked about electronic properties. They have these things of shape memory and other things you can do with them. And we have sort of this vision. If we got this spin polarized surface state, if I put in an electron and spin up, it'll go one way. Spin down will go the other way in that surface state, with the spin momentum locking. So this, for spintronics, will be a really interesting way to direct your spins, if we can get that to work. So what we want to do in the future is basically make up structures where we put layers of different Heuslers with different properties and try and make something unique. I don't know what we're going to make, but we're going to make something for fun. Okay, and we think it's really important. It could be good for spintronics. It could be good for other type of material properties we're interested in. So with that, I will thank you for your attention.
Any questions?
Topological insulators are great, but everybody's after topological metals now. So do you have any plans in that direction?
Some of these are supposed to be wild semimetals.
That's right.
Okay, so we also have this idea to look at the wilds on them as well, yes. So it's just much harder experimentally. So, okay, so one of the experiments we're trying to do now, we have built a vacuum suitcase so that we can take samples out of our system. Now it's a little harder with TSA to go to Sweden. So we're going to drive to Berkeley. Okay, shucks, it's going to cost me money. And we're going to take the samples and put them into a spin polarized ARPA system at Berkeley to try and measure. So, for example, if you grow a wild semimetal, now I don't need a cap. What we find, for example, we've grown platinum, lutetium, bismuth, which we think might be more interesting, but we haven't found a cap that works. But now we can grow it, put it in our vacuum suitcase. My students keep asking me for a rapid sample transfer system. What's that? It's called a Ferrari. To get from Santa Barbara to Berkeley quickly. Right? But the idea is to get it up there and keeping it in an ultra-high vacuum all the time, and then see if we can get this to work. So in fact, I will tell you, next month is our first real experiment to try that. So I think in 3 weeks we're going up to see if that will work. And then we can look for the Fermi arcs and all these things for the wild semimetals. Okay?
What is, you show us the magnetoresistance.
Yeah.
Very nice. What is the voltage dependence?
Oh, that's, okay. So that probably, if I went back, I have to go way back. That's when we do this. The voltage dependence depends what current you choose. I haven't got it. I don't have it here for this one. But if I go to the iron 3 gallium here, okay. So this is sort of changing the voltage. This is this is looking at our signals on the voltage dependence where we are. Depends where you are. On this one. And we can play games here with our detectors. When we do the bias detector, we can change the sensitivity as well.
Can you estimate the barrier out of this dependence?
That's a little tougher because there is a resistance in the channel as well. So it's a little difficult. I think this one here is difficult to get the barrier. Could be basically the effective barrier. If I wanted to measure the effective barrier, I would actually just do it with a single-sided and just do a simple IV measurements for that contact. Okay, that's what I would do. We've got it for this one here. The barrier, yes. Yes. Let's come down here. Where is it? I have it. Okay. Why can I never find my mouse again? Let's see if I can find it.
Your mouse is behind you. Right there.
The mouse is behind me, thank you. Let's see if I've got, okay. This one here, I can't, okay, let me hit unhide. Is it, it's in this one, isn't it? Is it left or right?
Yeah, I wasn't kidding. Yes.
Oh, it is behind me. You are serious. Okay, so let's see. let me just do this. And now if I put this one up. So, here's sort of, you'd extrapolate back from doing the IV measurements. So this thing here, this is actually, we were trying to look at the effect of manganese first, silicon first, etc. So the barrier height here would probably come out more like effective barrier height because of the high doping, probably more like 0.3 eV, something like that. 0.3 eV is my guess. We have done it up.
Where's the peak is?
0.7, because we're tunneling through. Because of the Schottky barrier, we made it thin enough that most of the carriers are actually tunneling through the barrier, but not at the Fermi level, but some distance up. So they're semi-Schottky like.
So you can explain to what is depending or not?
Yeah,
I think so.
Yeah.
From the IV.
Yeah, from the IV, yeah.
Get,
Not
slightly
idea.
non-linear.
Magnetoresistance.
Oh, the magnetoresistance. So that dependence, of that one I did show you, that funny dependence. Is that what you want? You're thinking? That's a little harder because it's also very sensitive to states that we've had as well. Because some of the things we've done before with iron, we actually got the signs start reversing on us. So there's some interesting things happening at the interface as well. Yeah. But the amount you measure also depends on how much current you have in how much the polarization of you're creating in the semiconductor compared to what's already in the bulk as well.
Just continuing with that same slide that you showed in your original talk, you had the iron gun, but the electrode is still the iron, but you were only talking about the interface.
Yes.
It's an iron 3 gallium.
No. For that one I had with the iron 3 gallium, way back. Where are we?
I
Iron
wonder
3.
if you
No, the
really
iron-
have your electrode as the...
Yeah, the electrode is iron. Okay, where was it? I went too far here. Okay, let's go. This one is all iron 3 gallium.
Oh, okay.
It's all iron 3 gallium.
Okay,
This is all iron 3 gallium.
okay,
Both of those. All of them are iron 3 gallium. All electrodes are iron 3 gallium.
okay.
Okay. So,
I see.
yeah. But this is a non-local measurement, don't forget. This is not its normal spin valve. It's a non-local spin valve measurement.
Any more questions?
So this is a voltage dependence you're concerned about. Yeah. Okay. So there are two things going on with everything we're measuring on this one here, is because one is what we're doing with this detector. Okay, the detector efficiency, as well as what's going on under here.
For this material that you compared arsenic and gallium-rich interfaces.
Yes.
But for later other material, the cobalt
Two magnets, second.
cobalt iron silicon, you didn't really mention here.
We tried.
4x4.
We tried the 4x4 surface of gallium arsenide only, and then we do know it reacted. Because it worked, we said, we're not going to go back and see if it's better with the gallium rich. That's the only reason we didn't do it. It was also a little bit more tricky to get the gallium rich surfaces to do it. So we just said, okay, let's keep what's working. But I would be interested to go back and see if we can go even higher if we do a gallium rich surface.
And for those two materials, did you do any spin without RPS to really measure or say
That's
is it really 100% or close to 100%?
No, we haven't. There's been two groups of measured spin polarization using photoemission. Okay, so Claudia Fels's group for cobalt to manganese silicon claims 93%.
Oh, that's
Okay.
good.
With her measurements, there's some work from another group in France, Andrew, I have to remember his last name now. His was very interesting. So his measurements showed that the polarization at the Fermi level was lower. And if you just put something on the surface, like a little bit of MgO, it went up. And the polarization was very sensitive to where you were close to the Fermi level. And just how you terminated it. So he was seeing higher spin polarization just below the Fermi level than at the Fermi level in his material. We've just done some work, not for cobalt 2, trying to do it with cobalt to manganese aluminum and iron to manganese aluminum. Not 100% spin polarized material, but there's some theory that if you do a superlattice, it's supposed to be, and we were trying to see if it was. So we just came back from France a week ago. So I have the data is a little new to see.
Any more questions? Okay, let's thank the speaker.
Beh.
Oh, you're welcome.
Thank you so much because I understand exactly the growth interface.
Yeah.